It turns out figure skaters know something about angular momentum as well, and actually they use conservation of angular momentum much to their advantage. Now, when I was younger, Dorothy Hamill was the famous figure skater out in the world scene, and she had won a gold medal in 1976, and in the 1980s she was out there doing lots of PR shows for Holiday on Ice and other things. Let's watch what Dorothy Hamill does when she's trying to do a twist, and you'll see how she uses conservation of angular momentum. So you notice in this little video clip here that she ended up speeding up very, very rapidly as she was spinning around like a top. And it's not that she somehow infused herself with more kinetic energy. She had the same amount of angular momentum at the beginning as she did at the end, and yet somehow she managed to make her angular speed go up really fast. So the question is, how did she do that? Well, the skater's on a nearly frictionless surface, so she's not being acted on by any external torques. And since there's no torque, the change in angular momentum over a change in time should equal 0. Or said another way, the angular momentum should not change. The angular momentum at a final time should equal the same as the angular momentum at an initial time. Or LF equals L0. But what she did in this process when she was spinning around is something like the diagram here shown it right. She initially had her arms extended very far out, and so she had a large moment of inertia, because moment of inertia increases with m times r squared, where r is the distance away from the axis of rotation wherever you have that mass. She wasn't holding barbells like in this diagram, but just simply having her arms and one leg out at a distance made her moment of inertia larger. When she pulled her arms and legs in, that means her moment of inertia changed. And so even though we have conservation of angular momentum, LF equals L0, we have to write out what L is. It's equal to I times omega. And if I naught was bigger than I final, then the omegas will change as well so that their product is constant. And that means that her omega, her angular speed, increased the moment she pulled her arms in. It doesn't mean that her angular momentum was changed, because angular momentum is conserved, but the fact that angular momentum is a product of I times omega and I shrunk means that omega went up, so her angular speed became very, very big. And you'll see ice skaters use this trick all the time. They can slow themselves down or speed themselves up just by simply moving their arms and legs in or out.